Assalamualaikum and greetings to the viewers. In this sharing session, me and my teammates Arif and Ilham will be presenting on our topic, which is CMOS 101 under the subject Analog Integrated Circuit Design EEP 4413. Throughout our sharing session, we will be focusing as stated. I will be presenting the introduction of CMOS and 3D structure of CMOS. Ilham will take over the sharing session with the explanation of each CMOS layer, while Arif will finish it with the explanation of each fabrication of CMOS. I will start with the introduction of CMOS. So, what is CMOS? So, definition. CMOS is a semiconductor technology used predominantly in integrated circuits or ICs, commonly referred to as chips or microchips. The foundation of MOSFET is CMOS transistors are based on metal oxide semiconductor field effect transistor technology. CMOS technology was invented in 1963 by Frank Wanless while he was working at Fairchild Semiconductor. CMOS is a combination of N-type and P-type MOSFET. So basically CMOS is a complementary metal oxide semiconductor. So basically two main MOSFETs are P-channel MOS and N-channel MOS. So PMOS and NMOS both use P-type and N-type semiconductors but in opposite configurations. PMOS has P-type for source and drain with N-type for the substrate. NMOS has N-type for source and drain with P-type for the substrate. Before CMOS, both PMOS and NMOS were standard. NMOS was preferred for being faster and cheaper but had drawbacks like static power consumption. So the advantages is that CMOS combines PMOS and NMOS in one IC. It offers symmetrical PMOS and NMOS pairs. This combination improves the design flexibility, reduces complexity, and minimizes electronic noise. CMOS requires less power because current is briefly applied when switching states, resulting in almost no power consumption in static conditions. Lesser power consumption translates to reduced heat generation in CMOS ICs compared to PMOS or NMOS based ICs. The application of this CMOS is that due to its benefits in power consumption and heat generation, CMOS logic is extensively used in microprocessor, microcontrollers, RAMs, image sensors, and more. It's expected to remain prevalent in the industry. And in computing terminology, you might also hear about the CMOS battery or CMOS setup. This refers to a small battery on a computer's motherboard that powers the CMOS memory, which stores system settings and BIOS configuration. So basically, if your computer's date and time keep resetting, is often due to a dead CMOS battery. In this next presentation, I will go deeper into CMOS, especially on its 3D structure. The image represented here presents a 3D design of a CMOS transistor structure showcasing both NMOS and PMOS transistors. Here's a breakdown based on the visuals. We have top view, 3D view, and also side view. So for the top view, this view provides a planar representation of CMOS layout. Poly represents the polysilicon gates of the transistor. Contact represents contact points where the different layers connect. Metal 1 represents the first layer of metal interconnects that connect different parts of the circuit. And plus diffusion and P plus diffusion regions where the silicon substrate has been doped with N-type and P-type dopants respectively to form source and drain regions of most transistors. And select and P-select are regions for the selective doping for the N and P-type transistors. And then well represents a region in the P-type substrate where N-type dopants have been added. This is where the P-type MOS transistors are formed to provide complementary operation. At the 3D view, it shows the perspective of the CMOS structure in 3D. You can see the silicon substrate at the bottom, which in this case is P-type. The M plus and P plus region represent the dope source and drain regions for the NMOS and PMOS transistors. Poly is the red regions that represents the polysilicon gates. SiO2 represents silicon dioxide, which is used as an insulating layer. M1 represents the first metal layer used for interconnections. At the side view, we have a cross-sectional view of the CMOS structure. It provides a clear look at how the different layers stack upon each other. This view helps in understanding the depth and layering involved in the process of creating CMOS transistors. In essence, CMOS technology involves the integration of both NMOS and PMOS transistors on a single chip. The NMOS transistor is faster and consumes less power when switching, but is weaker when on. On the other hand, PMOS transistors consume more power when switching, but provide a strong on drive. By combining both CMOS technology, we get the advantages of fast switching with lower power consumptions and strong drive strength.
Next, we will go to the general overview and explanation of the layers inside a CMOS fabrication. So these are some of the layers in CMOS when fabricating. So we will explain very briefly and generally of what does each layer will do and where it can be found. More on the details will be explained in the fabrication process when making these layers. Firstly is the substrate layer of a CMOS, where we will have two types of substrate, which is the N substrate and also the P substrate. The root for creating a CMOS is always the silicon wafer, where in the image above, we can see it is attached is the wafer on the right side. And each substrate will be cut off and polished from the huge cylindrical crystal of a silicon, and a CMOS will be built in on the P-type base of a silicon wafer. The next layer is the oxide layer, where an oxide layer is the protective layer of an oxide, which is formed on top of the P substrate itself. The main goal of this oxide layer is to act as a dielectric layer, which is made of silicon oxide in a very thin size, and it is used to separate the gate terminal of the MOSFETs from underlying source and drain terminals. Next is the formation of N well and P well. So for this formation, it will be either N well, which is an electron rich, or P well, a hole rich, where these wells will be applied on a wafer. And these type of wells also will have a specific region to be doped to form the N wells and also P wells. Next is the gate diode layer, where it is known to be a very thin layer of silicon dioxide which will be deposited on top of the wells that we have formed previously. So it acts as a dielectric material between the transistor's gate, electrode, and also the silicon channel. Since it will be acting as a diode, it will only allow for only one direction of flow as it blocks the reverse flow direction. Moving on next is the gate electrode, where we will have a polysilicon layer which will act as a transistor's gate electrode, and the use of it is to regulate the currents inside of the transistor itself. It is commonly made out of doped polycrystalline silicon. Next is the source and drain implants, where these dopant ions will be placed into the N wells and P wells region which we have informed previously, and this will create the source and drain regions of the MOSFET. Moving on next is the metal layer, where different type of metal layers will be deposited and patterned onto the CMOS itself, and it will create a connection between the transistors and components of the chip. A very common material used for the CMOS process is aluminum or copper. Moving on is the interlayer dielectric, which is the ILD. The ILD is an insulating layer which are created to separate the metal traces from each region, and it is also known to protect them from any damage from being occurred. Moving on is the contacts and via holes. So these holes or vias will be drilled into the CMOS itself, into the ILD, where it will connect the metal layers of the different layers itself. It will connect each metals into its underlying silicon or polysilicon layers. Lastly is the passivation layer, where this is the final layer of the CMOS, which will shield the entire chip from any environmental surroundings and physical damage.
Alright, hello everyone. Today I'm going to be explaining the fabrication process for the CMOS. Alright, step 1. We have to choose a substrate as a base for fabrication. Since we're making a CMOS N well, we start with the P substrate. Alright, step number 2 is that we do oxidization above the P substrate by exposing the substrate to high quality oxygen and hydrogen in an oxidation chamber at approximately 1000 degrees Celsius, which creates silicon oxide. So step number 3 is that we want to do selective etching. So the silicon oxide layer is subjected to the photolithography process. In this process, the wafer is coated with a uniform film of a photosensitive emulsion. Alright, step number 4 is we do masking at this certain area, but we leave certain area over here to be exposed to UV rays. So this will polymerize the substrate. Alright, step number 5 is that we remove the unexposed photoresist by using trichloroethylene. By using trichloroethylene, we will dissolve the unexposed photoresist. Alright, following for step number 6 is we etch for the oxidation layer, which we put hydrofluoric acid, which removes the oxide from the areas through which dopants are to be diffused. So step number 7 is the removal of whole photoresist layer, in which during the etching process, the photoresist mask is now stripped off with a chemical solvent of hot sulfuric acid. Alright, step number 8 is the formation of N-well, in which the N-type impurities are diffused into the P-type substrate through the exposed region, thus forming an N-well. Alright, step number 9 is we remove the silicon oxide layer by using hydrofluoric acid. Step number 10 is deposition of polysilicon. The misalignment of the gate of a CMOS transistor would lead to the unwanted capacitance which could harm circuit. So to prevent this self-aligned gate process is preferred where gate regions are formed before the formation of source and drain using ion implementation. So polysilicon is used for formation for the gate because it can withstand high temperature greater than 8000 degrees Celsius when the wafer is subjected to annealing methods for formation of source and drain. Polysilicon is deposited by using chemical deposition process over a thin layer of gate oxide. This thin gate oxide under the polysilicon layer prevents further doping under the gate region. Right, step number 11 is the formation of gate region, except the two regions required for formation of the gate for NMOS and PMOS transistors. The remaining portion of polysilicon is stripped off. Alright, step number 12 is oxidation process. An oxidation layer is deposited over the wafer, which acts as a shield for further diffusion and metallization processes. Alright, step number 13, masking and diffusion for making regions for diffusion of N-type impurities using masking process. Small gaps are made. So by using diffusion process, 3 N plus regions are developed for the formation of terminals of NMOS, as we can see here. So step number 14, the oxide layer is stripped off. Step number 15, we perform P-type diffusion. Similar to the N-type diffusion of forming the terminals of PMOS, P-type diffusion are carried out, as seen over here. So step number 16 is laying of the thick field oxide. Before forming the metal terminals, a thick field oxide is laid out to form a protective layer for the regions of the wafer where no terminals are required. Right, step number 17 is metallization. This step is used for the formation of metal terminals which can provide interconnections. Aluminium is spread on the whole wafer, and step number 18 is removal of excess metal. The excess metal is removed from the wafer. Right, step number 19 is the formation of terminals, and the gaps performed after removal of excess metal terminals are formed for the interconnections. And finally, step number 20 in making the CMOS N-well is that we assign the terminal names. Names are assigned to the terminals of NMOS and PMOS transistors, as we can see over here, the source, gate, and also the drain. So you might be wondering, how do we make a P-well technology of a CMOS? So the P-well process is similar to N-well process, except that here N-type substrate is used and P-type diffusions are carried out. but for simplicity, annual process is preferred. Alright, that's all for our presentation. Thank you very much for watching. Please like, subscribe. Peace.